Picture an electron scattering off a photon. Simple enough, right? A photon comes in, the electron absorbs it, continues on its way, and emits a new photon. We call this the scattering of light. But when we make the diagrams and calculations for scattering, we must include some peculiar possibilities. The electron could emit a photon before absorbing one. Already strange. But there's something even more bizarre lurking in the mathematics. The electron emits a photon then, and this is the really odd part, travels backwards in time to absorb a photon, and then proceeds forwards in time again. Yes, backwards in time. Not as some theoretical abstraction, but as a real measurable phenomenon. The path of such a backwards moving electron can be so long as to appear real in an actual physical experiment in the laboratory. Think about that for a moment. We're not talking about mathematical tricks or convenient fictions. We're talking about something you can detect, measure, verify in a lab. Now, when you observe this backwards moving electron while time moves forward for you, here's what happens. The backwards moving electron appears the same as an ordinary electron, except it's attracted to normal electrons. We say it has a positive charge. Had I included the effects of polarization, it would be apparent why the sign of charge for the backwards moving electron appears reversed, making the charge appear positive. For this reason, it's called a positron. The positron is a sister particle to the electron and is an example of an antiparticle. And here's where it gets truly profound. This phenomenon is general. Every particle in nature has an amplitude to move backwards in time, and therefore has an antiparticle. Every single one. Long before anyone understood why, Dirac predicted that in addition to electrons, there must be another particle, called the positron, discovered at Caltech by Anderson, that is necessarily related to the electron. The story of this prediction is, it's remarkable, really. Dirac simply followed where his equations led, even when they seemed to predict something impossible. All the properties of these two particles obey certain rules of correspondence. The energies are equal, the masses are equal, the charges are reversed. But more important than anything, more important, the two of them, when they come together, can annihilate each other and liberate their entire mass in the form of energy. Gamma rays usually. The positron is called an antiparticle to the electron, and these are the characteristics of a particle and its antiparticle. This wasn't just a theoretical curiosity. When Anderson found the positron in cosmic ray experiments, it confirmed Dirac's wild prediction and opened up an entirely new way of thinking about particles. The mathematics had predicted reality before reality revealed itself to us. It was clear from Dirac's argument that all the rest of the particles in the world should also have corresponding antiparticles. For instance, for the proton, there should be an antiproton, which is now symbolized by a P with a bar over it. The antiproton would have a negative electrical charge and the same mass as a proton, and so on. The most important feature, however, is that a proton and an antiproton coming together can annihilate each other. Now here's where people get confused, and well, it's worth spending time on this because it reveals something deep about what anti really means. The reason we emphasize this annihilation property is that people do not understand it when we say there is a neutron and also an antineutron. Because they say, wait, a neutron is neutral, so how can it have the opposite charge? You see? This question reveals a common misconception. The rule of the anti is not just that it has the opposite charge. It has a certain set of properties, the whole lot of which are opposite. Electric charge is just one property among many. The antineutron is distinguished from the neutron in this way. If we bring two neutrons together, they just stay as two neutrons. But if we bring a neutron and an antineutron together, boom, they annihilate each other, with a great explosion of energy being liberated with various pi mesons, gamma rays, and whatnot. The explosion is spectacular, precisely because neutrons have mass, quite a lot of it compared to electrons. When that mass converts to energy, according to Einstein's E equals mc squared, you get a tremendous release. The products aren't just simple photons like with electron-positron annihilation. You get a shower of different particles, a complex cascade of energy transforming into matter and back again. This leads to a fascinating possibility that, well, it stretches our imagination. If we have antineutrons, antiprotons, and antielectrons, we can make anti-atoms in principle. They have not been made yet, but it is possible in principle. The physics allows it. Only the engineering challenges stand in our way. For instance, a hydrogen atom has a proton in the center with an electron going around outside. It's the simplest atom, the building block of the universe. Now imagine that somewhere we can make an antiproton with a positron going around it. Would it work? Would it be stable? Would it behave like hydrogen? Well, first of all, the antiproton is electrically negative and the antielectron is electrically positive. So they attract each other in a corresponding manner. The masses are all the same, everything is the same. The electromagnetic force that binds ordinary hydrogen would bind antihydrogen in exactly the same way. The quantum mechanics that governs electron orbitals would govern positron orbitals identically. It is one of the principles of the symmetry of physics, the equations seem to show. That if a clock, say, were made of matter on one hand, and then we made the same clock of antimatter, it would run in this way. The ticking would be identical. The mechanisms would function the same. Every process that happens in matter should have an exact mirror in antimatter. Of course, if we put the clocks together, they would annihilate each other. But that is different. Keep them apart and they're indistinguishable. But now an immediate question arises, and it's one that shook physics to its core. We can build out of matter two clocks, one which is left hand and one which is right hand. For example, we could build a clock which is not built in a simple way, but has cobalt and magnets and electron detectors which detect the presence of beta decay electrons and count them. Each time one is counted, the second hand moves over. This isn't just a thought experiment. This is based on real experiments done with cobalt-60, a radioactive isotope. The setup is ingenious. You align the nuclear spins using a magnetic field, cool everything down to nearly absolute zero to keep the alignment, and then you watch which direction the beta decay electrons prefer to go. Then the mirror clock, receiving fewer electrons, will not run at the same rate. So evidently, we can make two clocks such that the left-hand clock does not agree with the right-hand one. Let us make out of matter a clock which we call the standard or right-hand clock. Now let us make also out of matter a clock which we call the left-hand clock. We have just discovered that in general, these two will not run the same way. Prior to that famous physical discovery, it was thought that they would. This was shocking, truly shocking. For decades, physicists had assumed that the universe was perfectly symmetric on the mirror reflection. Left and right should be equivalent, but they're not. The weak nuclear force, which governs beta decay, violates this symmetry. Now, it was also supposed that matter and antimatter were equivalent. That is, if we made an antimatter clock, right hand, the same shape, then it would run the same as the right-hand matter clock. And if we made the same clock to the left, it would run the same. In other words, in the beginning, it was believed that all four of these clocks were the same. Now, of course, we know that the right hand and left hand matter are not the same. So we lost one symmetry. The universe distinguishes left from right. But what about the matter-antimatter symmetry? Presumably, therefore, the right-handed antimatter and the left-handed antimatter are not the same. If left and right aren't equivalent for matter, they shouldn't be equivalent for antimatter either. So the obvious question is, which goes with which, if either? In other words, does the right-handed matter behave the same way as the right-handed antimatter? Or does the right-handed matter behave the same as the left-handed antimatter? This is the crucial question, and its answer reveals something beautiful about the universe. Now, you might think this is just an academic curiosity, but it's not. This goes to the heart of how nature works. We had to do very careful experiments with beta decay, using positron decay instead of electron decay. Beta decay experiments, using positron decay instead of electron decay, indicate that this is the interconnection. Matter to the right works the same way as antimatter to the left. The symmetry wasn't destroyed. It just got hidden in a more complicated way. You have to combine two transformations, matter to antimatter and left to right, to recover the symmetry. It's like a puzzle where you thought you lost a piece, but it was just hiding under another piece. Therefore, at long last, it is really true that right and left symmetry is still maintained. If we made a left-hand clock, but made it out of the other kind of matter, antimatter instead of matter, it would run in the same way. So what has happened is that instead of having two independent rules in our list of symmetries, two of these rules go together to make a new rule, which says that matter to the right is symmetrical with antimatter to the left. This combined symmetry, called CP symmetry for charge conjugation and parity, became the new foundation. The universe respects this deeper symmetry even while violating the individual symmetries. It's elegant, it's unexpected, and it has profound consequences. Think about what this means. We thought we understood how the universe worked. We thought left and right were the same. Then we discovered they're not the same. The universe picks a direction. But then, and this is the beautiful part, we find that if you flip both things, matter to antimatter and left to right, you get back to the same physics. The symmetry isn't lost. It's just more complicated than we thought. This has profound implications for communication with alien civilizations. Now, this might sound like science fiction, but bear with me, because this is a real problem. Imagine we make contact with beings on another world through radio signals. We teach each other our languages, our physics, our technology. We share our cultures, our philosophies, our dreams. Years of communication, decades maybe. Eventually we decide to meet face to face. But here's the problem, and it's a real problem. How do we define right and left across the void of space? We can't point. There's no up or down in space. No shared reference frame. We can't send them a sample. We have to describe it using physics alone. Pure physics. Nothing but the laws of nature. Before this discovery about parity violation, we couldn't do it. There was no way to distinguish right from left using only the laws of physics. But now we know. And now we know that we can use these beta decay experiments to do exactly that. We can say, look, build this cobalt-60 setup, align the nuclear spins this way, cool it down, measure which direction the electrons prefer to come out. That direction, that's what we call right. So if our Martian is made of antimatter, and we give him instructions to make this right-handed model like us, it will, of course, come out the other way around, because of that symmetry we just discussed. Their right will be our left if they're made of antimatter. We tell them, build this cobalt-60 setup, measure the electron directions. That defines right for us. They do the same. We compare results. If we get the same answer, we're both made of matter. If we get opposite answers, well, then we have a problem. What would happen when, after much conversation back and forth, we each have taught the other to make spaceships, and we meet halfway in empty space? We have instructed each other on our traditions and so forth, and the two of us come rushing out to shake hands. Both species excited, both ready for this historic moment. Well, if he puts out his left hand, watch out. That simple gesture, that one simple gesture, would tell us everything we need to know and give us just enough time to get away. Because if they're using right the opposite way from us, it means our physics experiments gave opposite results, which means they're made of antimatter. One touch and both beings, probably both ships, maybe everything in the vicinity, would vanish in a burst of gamma rays, the biggest explosion you've ever seen. All that mass converted to pure energy in an instant. So remember that. If you ever meet an alien, do not shake hands until you've checked the beta decay experiments. This brings us back to the fundamental behavior of these particles and the eternal cycle of creation and destruction at the heart of reality. When a particle and its antiparticle collide, they annihilate each other and form other particles. For positrons and electrons annihilating, it is usually a photon or two, sometimes more, depending on the energy. The energy that was locked up in their mass, all of it, every bit, gets released as pure electromagnetic radiation, traveling outward at the speed of light. Think about that. Pure conversion. Mass becomes energy, nothing left behind. The process is perfectly reversible. Just as matter and antimatter can annihilate to create photons, photons with sufficient energy can create matter-antimatter pairs. This happens constantly in particle accelerators, in cosmic ray collisions, near black holes, anywhere there's enough energy concentrated in a small enough space. It's happening right now, actually. Cosmic rays hitting our atmosphere, creating particle-antiparticle pairs. Most of them annihilate almost immediately, but we can detect them. And what about photons? This is interesting. Photons look exactly the same in all respects when they travel backwards in time, as we saw earlier. So they are their own antiparticles. You see how clever we are at making an exception part of the rule? A photon moving forward in time is indistinguishable from a photon moving backward in time. So it serves as its own antiparticle. Photons have no charge, no distinction between particle and antiparticle. They're perfectly symmetric in time, completely symmetric. Now, the backwards moving electron interpretation explains something remarkable that Dirac's original theory left mysterious. Dirac said there must be antiparticles, and he was right. But why? Why must there be antiparticles? His theory didn't really answer that. But when you think about particles moving backwards in time, suddenly it all makes sense. It has to be that way. When we see pair production, an electron and positron appearing from pure energy, we're actually watching a single electron's world line making a U-turn in time. Think about that. The positron isn't a separate particle that was created. It's the same electron, now traveling the opposite direction through time. One electron, just going back and forth in time. When we see annihilation, we're observing that same U-turn from a different perspective. What looks like two particles meeting and destroying each other is actually one particle's path doubling back on itself in time. The creation and destruction are illusions of our forward time perspective. We're stuck moving forward in time. So when we see something moving backward, we interpret it as a different kind of particle, but it's not. The electron never really appears or disappears. It just changes direction in time. like a car making a U-turn. Same car, just turned around. This picture, strange as it seems, it works perfectly. The calculations match experiments with extraordinary precision. We're talking about predictions that match reality to 1 part in a trillion, better than any other theory in physics. Every Feynman diagram we draw relies on this interpretation, allowing particles to zigzag through time, forward and backward, creating the rich tapestry of quantum interactions we observe. We sum over all possible paths, including the ones that go backward in time, and we get the right answer every time. Nature has spoken, and the mathematics is clear. Particles can and do travel backwards in time, and we call their backwards moving versions antimatter. It's not some exotic opposite universe material. It's ordinary matter, electrons, protons, neutrons, moving through time in the direction opposite to our experience. That's all it is. And that simple insight, that one insight, unlocks the deepest secrets of how particles interact, how they're created and destroyed, and why the universe has the structure it does. You see, sometimes the strangest ideas, the ones that sound completely crazy when you first hear them, turn out to be true. The universe is stranger than we imagine, and that's what makes physics so wonderful.